the meantime, yeah, so we have Bernd Lieber now, who is also already on the screen. He's the manager, sales and projects of OCHSNER Energy. And we will be having a presentation, also 30 minutes. The title is Decarbonization of Heat by Industrial Heat Pumps. And yeah, Herr Bernd Lieber leads the organization and sales at OCHSNER Energietechnik GmbH is an Austrian company and a pioneer in advanced heat pump technologies, and we're very proud to have them also as our partners. So the floor is yours.
Thank you very much, Ingo, for this introduction. You see the presentation screen, right? So everything's fixed so far. Does it work? Yeah, perfect.
Yeah, it works, yeah.
Yeah, perfect. Okay, yeah, thank you very much. Thank you also very much, Mr. Lindl, for this very good presentation. And to be honest, now you get so much electricity out of this ORC process, where to use this as electricity to bring back heat again. This is where I can connect on. And this is also pretty important for me to say that this is a very, very good combination of producing electricity with the ORC. And then also in the same area, you're able to produce heat with our heat pumps. And this is what brings me really to the first topic of my presentation. So the question is a little bit also about the city of the future. How would it look like? Nobody of us knows if we are flying around in the future, if really everything is that green, how it looks in that picture. We hope that it's going to get that way. But what is really for sure that the city of the future needs heating and cooling for the buildings, because we're still there and we need to get it warm in the houses, and even it's going to be a little bit more important for the future to cool it down. And in our thinking, it's pretty important to see this future and to connect all opportunities together, as it was already mentioned in the presentation of Orkan, is this sector coupling. So we need mobility, we need heat and cool, and we see that the connection of all these topics is the electricity. So it's really important to get the electricity renewable done. We've seen almost all opportunities today in the presentation of Kellag and now in the presentation of Orkan, how many different opportunities of renewable energy production for electricity we have. And one of the main topics when we see the heat area is to go on there with heat pumps. And this is also in our areas with these heat pumps, and especially when we have this cheap, almost €0 electricity production, it's really very short RE times for our customers' investments, what we have here. It's pretty important for me also to see or to tell you that heat pump is really a key technology for this future. Not only a new one, it's a pretty old one already. 2024, the head of Austrian Institute of Technology, R&D Center in Austria, Mrs. Bach, said that the discussion for heat pumps is already through. No way is going beside it. And it's not even last year's discussion. It's started early in the 20th century. So this, you see here, the Zurich town hall has been heated with the heat pump already in 1938. So before the Second World War, it was also already installed a large capacity heat pump in the town hall in Zurich. And as many inventions in the past were due to some obstacles, they appeared. Also here, the obstacle was that it was not possible to install a coal cellar in this town hall due to the fact that the town hall is directly near directly on the lake of Zurich, and therefore it was not possible to put this coal cellar in there. So they needed to have a different solution, and this brought up the heat pump solution there. And since 1938, it's not the first heat pump still running there. It's in the meantime, as far as I know, it's the fourth heat pump still running in this area. But you see, it's a very well-known technology who's pretty old, and that leads us really to this transition issue we face in Europe. And then we need to have an energy transition, as we all know it. And there is no energy transition without heat transition, and for sure no heat transition without heat pumps. It's really one of the main purposes we face in the near future. That brings me to just a short overview of how old this technology already is. It's pretty funny because Mr. Lindler has shown almost a similar topic because the ORC process is working after the same process as we have it here in the heat pump. It's the Carnot cycle. It's just a different output. So we need the electricity in this circuit to get the heat out of it. But I try to just explain it. It's similar. It's a Carnot process, and Mr. Carnot lived the end of 18th and early 19th century, and this is the heart of the heat pump, and it's also the heart of the fridge you have in your home. So it's just the heat pump is working same like your fridge at home. We're just using the other side. So in the fridge, you cool down the inner side of the fridge, and you heat on the back of the fridge, and so you take the cool side of it. And with the heat pump, you use the warm side of it. In that specific case, it means you take the back of the fridge because you need the heat in the house. Usually, you can also use it for cooling, but mainly it's used for heating. I don't want to go into this detail because Mr. Lindl already described it with expansion and evaporation and condensing it, everything. And we are using for this compressing the refrigerant we are using in this cycle. We need this electricity, for example, also from an ORC or other renewable systems. And we, during this condensation, bringing the heat into the house. Just a short introduction over the heat pumps. We, as OCHSNER, are a very old company already. So we were founded in 1872 as a copper mill in Silesia, today's Poland. And we're still a family-owned business. So Mr. OCHSNER is my company boss and head of the company, still in the 5th generation. And his grandfather was, during the Second World War, coming to Linz, where he founded OCHSNER Pumps in Austria. And from 1946 to 1992, we manufactured process pumps for the International Brand Engineering. And already in 1978, Karl OCHSNER Senior invented the OCHSNER Heat Pump GmbH. So we have over 45 years of experience with heat pumps already. We started in the early 18 with domestic hot water heat pumps, and then went into the heating heat pumps before we started early 2000 with industrial heat pumps already. So we see us here really as an international technology leader, and we're still producing in Austria. So we have all our production plants, 3 of them in Austria, where we have European quality, European employees. So that's very important for us also to mention this and that side. We already have seen some climate change reports also during the presentation of the European government. And it's very important to not heat up our Earth anymore. And this brings us really to the most important things, that we have to protect our environment with no combustion, with shifting also away from throwaway culture towards a willingness to repair. This is because we have our own customer service people, as also mentioned by Mr. Lindl. It's just so important to get well-known suppliers that they are able to repair something and not throw away everything is also one of our main goals to lift that. And this we can tell it because we have over 20, 25, or even 30 years lifetime for our heat pumps, because they're like a fridge. When they once running, they just running. So it's very, very important. For the market opportunities, it's also very important to have a deeper look on it, because many of you may know the standard air-to-water heat pumps or water-to-water heat pumps for the household. So the smaller sizes up to 10, 20 kilowatt of heating capacity. Many of you may also know some larger capacities, also air-to-water up to 100 kilowatts. But what we are talking now, we are also going for new opportunities in the source side. So beside the geothermal groundwater and air-to-water heat pumps, we also use sewage water as a source for our heat pumps. We use waste heat, similar like the OC process out of the chimney of biomass plants. We use this as a flue gas condensation in this case. We need refrigerant, we use refrigerant networks or the waste heat of server rooms to heat up, to take it as a source for the heat pump to bring the temperature again to a useful temperature for the customers. And almost everywhere we find opportunities to simply install it in that. We have also already heard today something from the European Union regarding the temperature areas we are already in. The Fraunhofer Institute made a study a few years ago about the heat demand of the German industry for process heat applications. And you see here in this picture the different industries, like the textile industry, steel work is in the middle, wood, non-metal, food, up to chemicals and metals. And you see on the right-hand side in this table the temperature areas. And as you can see, until the yellow one, you go up to 200 degrees C of demand of temperature, what they have. So the chemicals and the metals have very much higher temperature, but around 115 terawatt hours thermal power per year of process heat in the temperature region below 200 degrees C. And this is a study only for the German industry. So we have even, when we're looking over all Europe, it's even much higher. As you can see, it's 1,920 in this area needed in the entire European Union. But you can see it's a very big opportunity for this process heat pumps where we are almost already there. At the moment, because we are trying to look on serial production, have heat pumps up to 120 degrees C. But there are already the first projects where we also look above, and there are some other competitors. They are already at 160 degrees C, for example. So this is the future, and we have to have a look in this, because these are the main opportunities where we have waste heat and where high temperature heat is needed again. So this is really a huge demand what we have to decarbonize in the near future. When we're looking at our products, just a very short overview that you can see where we are in. We have opportunities for heating, for domestic hot water, and for cooling. This is the standard room heating concept. We have the capacity area starting from 2.2 kilowatt, which is a standard hot water heat pump, which anybody of you can do in your cellar and producing heat water with the heat pump, to the standard heating heat pumps up to 100 kilowatts, up to 82 degrees C. So this is a standard heat pump with very less place to install. And then we come to the more special projects where I'm the head of this industry part, where we have these high capacity heat pumps up to 1 megawatt. I'm talking in this area about thermal power, so I don't need so much electricity to reach this 1 megawatt. This could be also a good combination for the ORC cycle, for example. But in this area, we're producing heat up to 120 degrees C in specific. When we're talking about the industry solutions, we have heat pumps for industry, process heating, so all these demands we've seen before. And OCHSNER Energietechnik is an associate company to the OCHSNER heat pumps, and we are already manufactured our first heat pumps in the early 2000s. So 2002 was the first own manufactured heat pump in Austria for the industrial sector, and we are doing this. We started with standard house heating, and we're doing 90 degrees C since over 10 years already. And the 120 is the newest, so we're doing 120 since 5 years in this area. We are working with screw compressors and shell and tube heat exchangers because they are more robust in these systems where we are, because we're talking about life cycles or running times of a heat pump. A standard heat pump in a household has a running time of about 1,800 to 2,200 operating hours a year. We in the process area talking of 6,000 to 8,000 even hours, operating hours per year, which where we need to have very high efficiency and also robustness for all these suppliers or all these parts in the system, and therefore we are looking for screw compressors and shell and tube heat exchangers to have these robust systems. Our heat pumps, or the heat for our heat pumps, can be used in all types of buildings, infrastructure, industrial processes, and food processing, and so on, and many, many more. And as already mentioned, we also, for example, use sewage water out of the main sewage channels, so of the large ones, but also we have some small ones. So the heat pump, for the heat pump, it doesn't matter where the heat is coming from. It's just important that we have a particularly temperature there. So, but we can use from 0 degrees C up to 60 degrees C as a source, and then bring it up to the temperature the system or the process needs in this area. And similar to the ORC process, everywhere where cooling tower is installed, this can be replaced by using it as a source for a heat pump. So it's really a similar process, it's a similar opportunity. In my point of view, it's not even either or, it can be really an and. So you can use, we also have heat pumps installed in systems where we have 4 heat pumps and in addition 1 ORC system installed there, so we can use all together, and it's even better because the electricity is produced on site, and for this we utilize the high waste heat with this high temperature consumption in this area. Just a short overview, we have different series in this industrial range. So we have an average temperature is up. When we're talking about this average mid and high temperature, we're talking about the heating temperature. The average temperature goes up to about 70 degrees C, the mid temperature up to 90, and the high temperatures up to 120 degrees C. They're manufactured all and planned all on site in Austria, and then delivered to the customer how they where they want to have it. I want to show you also some references where we are in, and that you have a better view what opportunities you have, and maybe you see one or the other opportunity also for your plant or for your building, and we can talk afterwards a little bit more in detail about these opportunities, or even after the conference. The first is a standard heating, but I don't want to not show it in this case because it's a standard heating and cooling in Germany. So this is the castle in Berlin. It was rebuilt because it was destroyed during the Second World War. Was completely rebuilt, and we delivered in 2016 2 heat pumps with 250 kilowatts each for heating and cooling. And in this area, we have this building was rebuilt on piles because it's there in this water area where they needed to build piles in there. And the big advantage is for the heat pump, they installed energy piles. So it's nothing else like a standard ground pile, but they used it as the fundament of the building itself. And so the source, the building of the source was for free because it was they needed it to do it anyway. And therefore we have a ground source heat pump with no extra costs for the source side of the heat pump, and they earn money from the first day on because they have less investment even than the gas, for example, over there. And we are heating this building and cooling this building all year long. This is a very simple reference for our building heating system. When we're talking about booster heat pumps, I brought a reference from a hospital in Austria where we have installed 2 medium temperature heat pumps. So they are producing 60 degrees C for the heating of the building and the cooling. And for the hygienic safety in the clinical areas, they need higher temperatures. And therefore, we installed 2 booster heat pumps with 60 and 80 kilowatts who take the source, the heating temperature, the 60 or in this case the 40 degrees C as a source, and bringing it up to 75 degrees C. Just this part of the whole, so you don't need to heat up the whole buffer tank. So you just take this part where you need this higher temperature and bring it up to the mentioned temperature for 75 degrees C in this area. And this is done with our P2D series because this is a very small heat pump in the size. So it's 70 by 70 centimeters and 2 meters height and can produce up to 130 kilowatt thermal energy and reaches up to 80 degrees C, which is really very perfect even in sites where we already have to renew the system. It's pretty easy to install even there. Just a small, this is also a little bit for me that you can see it afterwards when you have the presentation. You can see a schematic how it looks like. Another waste heat recovery system, and this is just a small looking over your own borders, but it is looking over borders because there are some sites in this world, for example, data centers. Data centers need to be cooled all day long, and many of the data centers don't need their own waste heat to bring it back into the system. So data centers have to look in the neighborhood if anybody of the neighbors is able to use this heat. And we have a very good example for that in Switzerland, where we have a cheese manufacturing site, which is almost directly beside the data center. And they connected them together. So the data center produces waste heat of about 20 degrees C in this area. And the cheese factory has an energy demand of approximately 1,800 megawatt hours per year because they're producing 10 million liters of milk and 300 tons of cheese per year. So they have different temperature areas also what they need, and the big advantage is that the waste heat of this data center is now sold to the district to the cheese factory and is delivered there through a district heating network. So they are delivering this 20 degrees C from the data center, which is the waste heat, over a district heating network to the cheese factory, and this is then the source for the heat pump. So we have a 20 degree source where we get this from the waste heat from the data center, and then there is installed 500 kilowatt heat pump, which brings this 20 degrees C up to 90 degrees C, what they need in their process. They have in addition also 2 gas boilers because they need for some processes temperatures of 130, 140 degrees C, and this is where they lift up this temperature with the gas boiler. But the base with the 90 degrees C is done with the heat pump. And this is what you can see, that sometimes you also have to look in your surroundings. If some of your neighbors have waste heat they don't need, if you don't have it on your own, for example. So this is a very good example in my point of view, where you can see, have a look over your own borders, and we can fight together for a renewable energy usage in this whole system. It's a very, very good example for that. Another reference, also in this case, is a building, also a data center. It's a little, the installation is already a little older. It's 12 years, so it was installed 2013. This is the Vattenfall city in Hamburg, where they have the data center, and this building has one specific: it needs heating and cooling all year long. So they need heat even in summer times, and they need cool even during the winter period. Till this installation, they had a district heating and district cooling installation there, so they have no own systems. And for this, the heat pump is a huge advantage, because there were installed 2 heat pumps with 400 kilowatts each. And we're using the cold side as a source and delivering it to the warm side. That means we have the base load in this area, the magenta one is, because the blue one is the cooling demand over the year, January until December, and the red line is the heat demand. And the heat pump work is the magenta area, where with the heat pumps we deliver the base load all year long. And you can see that during March we have an 80% coverage of the cooling, and we have almost only along 25 to 50% coverage of the heating demand in this building. And with these specific topics, we have the COP, and you may have heard of the COP. It's the efficiency of the heat pump, the coefficient of performance, how it's called. And in this specific area, we have a COP for heating of 4.3 in average, and above 3.3 in this area for cooling. And due to the fact that this heat pump produces cooling and heating, which is used at the same time, you can add these 2 figures. So we have an average COP of this whole system of 8. This is an efficiency of 800%. So you produce, out of 1 kilowatt hour electricity, you produce 8 kilowatt hours heating and cooling. And with that big efficiency, you can lower your return on investment time to less than 3 years, which is amazing in this specific area. And the last reference I want to show you is similar, like we've seen it in the ORC circle before. It's the waste heat recovery out of a biomass district heating network. We already have seen the net zero emissions CO2 deal of the EU, because this was the reason for this specific project. They wanted to increase the renewable energy, wanted to minimize the consumption of CO2 certificates, which we have to pay here in Austria. It's a project in Austria. And they want to increase the cognition capacity of the biomass cognition plant. And therefore, they made an overview. You see here in the inner circle the heating labeling of the plant before. So they used almost 64.7% biomass, and 10% was produced via gas. And after the project, they even increased the biomass percentage up to almost 67%. and they are now making 16% of the heat with heat pumps, and only 1% is remaining with gas. What they have done is they made a measurement regarding the volume flow and the humidity in the flue gas, and measured the available latent heat after the first heat exchanger they already installed, and then made the completely planning, and they found out that they still had a waste heat of 3 megawatt. So they were usable latent heat in this exhaust gas stream was 3 megawatt. They wasted every hour. And out of this 3 megawatt, with electricity need of 0.8 megawatt for the heat pump, they installed 4 heat pumps with 1 megawatt each, and are now producing out of this 3 megawatt exhaust air. They produce 4 megawatt thermal power with the heat pumps. And the very interesting thing is that because we have 2 additional heat exchangers installed, and out of these heat exchangers, you get different temperature areas. One time you get 44 degrees C, and the last you get 32 degrees C. And you can see it in this schematic where we have this flue gas condensation. Here is the biomass boiler on the top, and this is the chimney on the left-hand side. You can see here there were already installed 1 flue gas heat exchanger in 2011, where the outlet temperature was 65, or is still 65 degrees C. And this 65 degrees C can be used directly as hiring the return flow for the biomass boiler, which means you need less biomass to produce the heat. And this was already installed in 2011. And then it was planned this additional project where we installed 2 additional heat exchangers in the chimney with this lower temperature outlet, so 44 degrees C and 34 degrees C, which means these temperatures cannot be used directly. So they were now used for the sources of the heat pump. So there were installed 2 heat pumps with a source temperature of 45 degrees C and 2 heat pumps with a source temperature of 35 degrees C. And all of these heat pumps higher the temperature up to 65 degrees C, again to raise the temperature of the return flow of the biomass, which leads to this calculated costs of investment of 1.6 million euros. They were calculated savings of 440,000 euros per year, and the certificate cost savings additional 100,000 euros per year, so you have a payback period of less than 3 years. This was calculated in 2019 and 2020, and due to the fact that the Russian war began, the payback period was in this case even below 2 years, but this is the standard calculation I want to show you because it's a little bit a better view. This is the plant, so it's a very small room which was built in there in the cellar, and these 4 heat pumps were installed. So really a narrow installation of all these heat pumps. And here you can again see the weighted COP, because with the 2 heat pumps with the higher source temperature, you have a COP of above 5. And with the other 2 still above 4, so you have a weighted COP, so efficiency of 465%. So you get out of 1 megawatt hour electricity, you got 4.65 megawatt hours heat. And this is a very, very short return on invest time, what you have seen before. At the end, I just wanted to show you some videos. You get them afterwards because they're in German. They are the opportunity to have subtitles in there is better, so you can see it afterwards there in our YouTube channel. Just wanted to let you know that we have them, and it leads me to the end. I want to close with the picture at the beginning. We don't know how the future, the city of the future really will look like, but we believe that they will be heated and cooled with heat pumps from OCHSNER. Thank you very much for your attention, and looking forward to the panel discussion where we can also answer some questions or even afterwards.
Yeah, super. Thank you very much.